So I'm going to show you these 4 websites that I'd like you to look at. So here's the physics classroom explaining Kepler's 3 laws. As I mentioned, lots and lots of websites do that. So here is the first law, and it gives it away, how it's supposed to look like. And I will have a comment on the word ellipse later on. Law of equal areas. That's the second law. I also have a comment on that because I like to express it differently, and you'll see why. And law of harmonies. I don't hear that very often. It's simply called Kepler's third law. And one of the things that happens here is, you see this number in the back here for all these different planets. This number in the back here pretty much says 1.00. Yeah, sometimes it's a little bit different, right? But that's because there are certain measurements in the front here. So that's why not all of these numbers are exactly 1. And you will see that when you actually do my exercise as well. Also notice that at some point, as it says t squared divided by r cubed, I expressed a little bit different. I actually do the cube first and then divide by square, and still I come up with the same numbers for different objects. You will see that soon. Right, so from this first website, which I think I called website A, I'm going to go to what I called website B. This one here is on a website called Desmos, and it's really cool to graph things on. I didn't produce this one. Somebody else did, and I know not much is fitting on the screen here, so I click the play button and notice what happens. These planets are orbiting. So the person who wrote the script did it really well. I just adapted it because I wanted to have them orbit counterclockwise as we're looking at that, because that's usually the way you see it, because we're looking from the north. There's certain things you can do with that. You can use the scroll wheel and you can scroll out, and then you see Jupiter and Saturn, and they're also orbiting, or you can scroll back in, or you can shift it, and certain other things. You can even change the time. So if I stop the time here, I can actually go in here and say, hey, make it faster. So for example, like this here, and then I click the play button, and then you should see that they're orbiting quite a bit faster, right? So you can play with that, around with that quite a bit, and don't worry about when you change things. It's not going to be saved anywhere unless you're copying the link for yourself. So you're not going to mess up anyone's work here in Desmos. All right, so let me go to what I call website C. So this one I actually made. So, and again, you cannot, if you play with it, you cannot mess it up. So you can do certain things with this one here. For example, you can go over here and you can click on these here and notice that Mercury's orbit just turned off, and you can take the label away. You can turn the sun off. Okay, I know it's out of picture because my software here is so, the video software that I use is so small here. And let me take Mars away. So we're only going to look at Earth and the sun here. And look at the orbit of the Earth. Aren't we taught from Kepler's first law that we're orbiting on an ellipse? You find it in every astronomy book. Yes, we do. But our ellipse is so close to being a circle. Oh, I forgot to turn Venus off, right? Here. Oh, I turned Venus off. It's so close to be a circle that you can't even see that ellipse. You have to really zoom in very carefully. I'm going to turn, clicking on these little symbols here, I'm going to turn Earth actually off, and I'm going to turn Venus on. There it is. And now look at Venus orbit. It is actually an ellipse, but you have to look really close to actually see that. Here's Mercury's. Mercury is actually the most elliptical one of all planets, but I just turned the sun off because it wasn't in the center, right? And wow, that really looks like a circle. You have to measure really careful to actually see that it's a very slight ellipse. I'm going to turn the sun back on. And that the sun is not in the center of the orbit, that's a giveaway that it's not exactly a circle. But anyway, keep that in mind. All right, I'm going to go on to website D, which is the coolest of all. That's the solar system simulation from PhET, Physics Educational Technologies. So here it is, and this is the way that it opens, and I'm gonna take this little slider, I'm gonna push it all the way over to accurate, which means it's gonna be relatively slow. I'm gonna hit the start button, and I have this pink object here, I guess we could call it a planet or an object, either way, orbiting the yellow object, which is, I guess, kind of looks like the sun, right? So that object orbits the yellow object, but notice what the yellow object is doing. It also seems to orbit on this tiny orbit, right? Well, that's gravitation. The two are attracting each other with gravity. So as the pink object orbits around the yellow one, so does the yellow one. Of course, smaller orbit because it has more mass. You can play a lot around with this one here. So I'm going to reset this one here, and I'm going to change something. I'm going to change this one here to, let's say, 66 for velocity. And notice a moment ago, we actually saw kind of like a circle, but watch this. There it is, right? There's the ellipse. So depending on how you do it, you come out with something that looks like a circle or something that looks more like an ellipse. Also, what you clearly here see is Kepler's second law. What happens during one orbit of the pink object or pink planet? Well, when it gets closer, it's faster, and when it's further away, it's slower. That makes total sense because when it gets closer, gravity attracts it, speeds it up. When it's further away, gravity attracts it back and makes it slower. So, hey, I got that one across. I'm going to stop this one here. I will reset this, and I'm going to take the tape measure that you can see here. I'll use it here in a moment. And then I'm going to pay attention to the time. I think I'm also going to change the velocity here back. Okay, I'm going to hit the start button. And then I'm going to wait for one orbit until there. So I have one orbit. I'm going to jot down the time, 4.8. These are arbitrary units. By the way, that means that they really don't tell us if that's in seconds or hours or something. So I'm going to put then the ruler on here and see how wide that is. Ooh, almost fits, right? So I'm going to push that a little bit back. So it looks like I have 201 and 4.8. I will show you very soon what I'm going to do with those numbers. Actually, turns out I just double checked. I'm not going to show you what to do with these numbers because I made a slight mistake. I just double checked on something else. And what I want to do first is I want to change the mass of the yellow object here, the sun. So I'm going to make it heavier. That has a reason. You'll see it in a minute or so. So I'm going to click the start button. And now the mass is larger, which means that it's more attracted towards it and it should be faster. In fact, it is 3.7. That's what I'm going to use. And the distance here should be a little bit less, and it is. So I'm going to use the 3.7, and the distance is 185. So even I make mistakes, right? That's why I had to repeat this one. By the way, this 185 is actually the diameter of the ellipse. Technically, I should divide it by 2 to come up with the average distance, but oh well, I'm just going to leave it like that. Anyway, this is what I'm going to do with it. I'm going to use a calculator. Apparently, this is Google. Well, turns out Google itself is a calculator. So I'm going to do 185 cubed divide by 3.7 squared. Why? Because that's what Kepler's third law says. And the cube, of course, means I multiply 185 with itself 3 times. And the square means I multiply 3.7 with itself twice. And then I divide the two by each other. And I come up with this number. I'm going to round it to just 463,000, all right? And I'm going to post it within the data sheet that you're going to have available. And now let me show you what you actually have to do. You have to, in this applet here, go to Select Preset, scroll down, click on ellipses, and you actually have 3 of them, and you will measure the distances of these 3 orbits. And you will measure the times. Remember that the distances you can measure like this one here. So Notice the pink planet already made one orbit here, and if you wanted to stop for the blue planet, well, it's a little bit back, so it's a little bit less than 7.9. And for the green one, you would have to wait a little bit, and for the distance, you would have to measure across, all the way across here. And then you would have to write that down here. Ooh, I'm a little bit offshoot, so it's a little bit less than 15.3. These are the ones that you actually would have to measure. And I'm actually plugging those already into the table so you can confirm what you have. And you would have to figure out when you take this cube and divide by the square of the two numbers from each other, if you come up with the same thing or something very close to show, hey, this is how Kepler's third law works. By the way, notice the mass here of 250. That's why on my last one, I changed it from 200 to 250 to make sure that, hey, those are actually the same. And the other thing that you see here is all these ellipses, they seem to touch over here. In a real solar system, they really don't do that. So they just made a special case of this one here. Maybe they had a point of doing that. Anyway, enjoy this project.